All right, so welcome to the end of week 2 here. Today's plan is to look at the trig functions and really investigate the patterns and what we see. And I'm going to kind of give you the tips for how you can learn that entire chart by only knowing a very little bit of it. And once we do that, then we'll start looking at these functions as functions and start talking about domains and ranges and what their graphs look like and their intercepts and all that good stuff that we've talked about before, or that you've talked about before with functions. Okay, so let me go ahead and start by sharing my screen, and I want to go ahead and share with you a completed one of these charts. Now, I did put this up onto Canvas. If you go to the files tab on the menu, it'll pull up all the different files that are there in the class, and this is one of them. It's called completed trig chart or something like that. I try to name things exactly what they sound like as well, but this is what you'll see if you pull that up. So this is the exact same thing that we developed last time. It's just already all put together for us. So again, you'll see we have all the different degrees for the different angles and the corresponding radians. I'm going to start concentrating on radians. Okay, I want you guys to start thinking radians, plus it helps us with the patterns. And then these are their respective values of the sine, cosine, tangent, and so on. So let me just remind you really quickly some of the things that we learned about these. First of all, the sine, that was the y coordinate of the point. So if we had a point x, y, sine was the y coordinate and cosine was the x. So given a point that's on a unit circle, the y coordinate is the sine value and the x coordinate is the cosine value. Super easy. All right. So then tangent, that was defined as y divided by x. And then all the other ones were just the reciprocal. So I'm not going to bother writing them down here, but cotangent was x over y, secant was 1 over x, and cosecant was 1 over y. So that's how we actually got these, was by looking at the coordinates of the points on the unit circle. It's just these were nice angles. These were angles whose x and y coordinates we could find pretty easily because they come from nice shapes geometrically. And then we bounced into the other quadrants. We went all the way around the circle using the symmetry, and you notice that a lot of things were the same. They just changed signs, plus or minuses. Okay, so first, let me help you with a way to remember these guys, because as I told you, this is the only piece that you need to know. This little chunk that I kind of shaded in blue, because if you know that one, you're going to know the rest. All right. So, and we'll talk through very specifically how you know the rest once you know those. But first, I want you to notice that there's a little bit of a pattern with these. Notice how all the three values that are between 0 and 1 have a 2 in the bottom. So they're all fractions with a 2 on the bottom. Well, that's actually how you can remember what these things are. The first one is the square root of 0 divided by 2. Square root of 0 is 0, divided by 2 is 0. The next one is the square root of 1 divided by 2. Square root of 1 is 1. Then we get square root of 2 divided by 2, square root of 3 divided by 2, and then lastly, you get the square root of 4, oh, no, 9. Let me change that. That looks a little bit like a 9. It's the square root of 4 divided by 2. So kind of cool little pattern, huh? It's totally a, there is no reason for that. It happens to be. So that's a really easy way to remember this little column. Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Okay, so that's how you can remember this little chunk. So let's talk about how we can get the other ones from this. Now, cosine, let me just remind you the cosine values. So the next little set over here, these guys, these are just those sine values, but in reverse. So that should be nice and fast and easy. All you got to do is swap them out. So if you're going from 0 down to 1 with sine, you're going to start with 0 at the bottom and work your way up to 1 for cosine. So that's how you get that chunk. All right, now once you know sine and cosine, we can actually get secant and cosecant really easily. So what I'm talking about that are these two. Because how are you going to get, say, the secant values? What from over here tells you the secant values? How about this? How can
The
you use?
hypotenuse over the adjacent side.
Okay, so it's hypotenuse over adjacent, but we don't exactly have hypotenuse and adjacent and all that, right? But let's remember the reciprocal nature. Remember the big three, sine, cosine, tangent, tell you the other three because they're the reciprocals. So secant is 1 over cosine. So see all the ones that are in the yellow? If I take 1 and I divide it by these, 1 divided by 1 is 1. 1 divided by half is 2. 1 divided by 0 is undefined. 1 divided by root 2 over 2 is root 2. All right, but you can get the secant column just by taking the reciprocal of the cosines. And you get cosecant by doing the same thing with the sines. Okay. So if we really wanted to think about this just as going from sine, you take those sine values, find their reciprocals, that gives you cosecant. And then the secants, you can just swap them, just like we did with sine and cosine, because we saw with the cofunctions, that's why they're called cofunctions, that the angles that add up to 90 degrees or add up to pi over 2 have the same cofunction. Okay, so now that leaves tangent and cotangent. So I'm going to give you another little fact here that we haven't talked about before, but this is another identity. And what this identity is, take a look at tangent. Remember down here how tangent was defined? It was the coordinates y over x. So you took the y coordinate and divided by the x coordinate. Well, the y coordinate was your sine value. The x coordinate was your cosine value. And so from that, what we get is that tangent is equal to sine over cosine. So if you want to get the tangent numbers, all you have to do is take the sine and divide it by the cosine. Check it out. 0 divided by 1 equals 0. So I can even put a little divide by thing right there, right? Or come down to 45 degrees, pi over 4. I have square root of 2 over 2 divided by square root of 2 over 2. Well, anything divided by itself equals 1. All right, root 3 over 2 divided by 1/2. You just flip that thing over and multiply because it's a fraction, you get root 3. So that little division is how we can get the tangents. And then once we know the tangents, you just reverse them, and that gets you the cotangents. All right, so check it out. If you know just those ones in the blue, and I gave you a nice little pattern for it, you can develop all the rest of the top. All right, so cool. That's useful. But what about the rest of this? All right, well, for the rest of it, we're going to break it into chunks. We're going to look at the angles that are between pi over 2 and pi. So we'll kind of do those in purple, right? Now, notice that all of these angles, these are in quadrant 2. remember your quadrants. And quadrant 2 are the angles that are bigger than 90 degrees and less than 180. So that's these guys. And the thing about the quadrant 2 angles is if you look at the pluses and minuses, the pluses and minuses are the same for each one of those angles. Like notice it here, the sine is positive for all of them. Cosine is negative for all of them. Tangent is negative for all of them, and so on. So the quadrant 2 angles all share the same plus or minus sign. All right, well, if we go down to quadrant 3 angles, they're the ones that are between pi and 3 pi over 2. That's these. I want you to notice that again, with the plus or minus signs, within this quadrant, they're all the same. All the sines are negative, all the cosines are negative, all the tangents are positive, and so on down the line. Now, they're different than quadrant 2, right? The quadrant 2 angles had, say, negative tangents, where quadrant 3 have positive tangents. But at least within that quadrant, we have consistency for the different trig functions. Okay, well, that leaves us then the fourth quadrant, and I'll make these guys orange, let's say. So between here and here, these are guys that are in the fourth quadrant. Same deal. Within this quadrant, in the different columns, the signs, plus or minus signs, are the same. So sines are always negative, cosines are always positive, tangents are always negative, so on down the line. All right, well, this is how we're going to remember the rest of these, because we already saw that it was copies. It was copies based on which of these first quadrant angles it was similar to. And it was really easy to tell, especially in radian form, because you can use the denominators of the fractions to tell you that, right? So like pi over 3. If you look at the other ones that divide by 3, so 2 pi over 3, 4 pi over 3, 5 pi over 3. And if you were to look at those rows, all of these rows look identical with the exception of the pluses and minuses. So all we have to know is what's the pattern in the different quadrants. All right, so let's look at the big three. And for the big three, notice that there's always one that's different. Like in quadrant 2, in those columns, sine was positive, cosine and tangent were negative. So sine is the one that's different. In the third quadrant, sine and cosine are negative, tangent is positive, right? So tangent's different. And then similarly in quadrant 4, it's the cosine that's the difference. So really all we have to remember is which one of them is positive, because there's going to be one that's positive and the others are negative. All right, well, what that does is that gives us a nice little mnemonic device. And let me share that with you real quickly here. So again, remember these are quadrants 1, 2, 3, and 4, right? In that order they go, again, counterclockwise. So just think when we're in standard position with angles, the order that we hit them. So quadrants 1, 2, 3, and 4. And the mnemonic device is all students take calculus. I guess we could also say all students take class, but everyone should take calculus. All right, well, here's how this works. Look at the first letter. All right, so all. What that tells me is in quadrant 1, all of them are positive. So if you go back and you look at how they were defined, it makes sense that they're all positive. The x coordinates and y coordinates there are positive. And since all the trig functions come from those coordinates, they're all going to be positive. Okay, so then the students, that S stands for sine. So that means that in quadrant 2, it's the sine that's positive. And this is for the big three. Okay, so sine is positive, cosine and tangent are negative, which then means we know what happens with the other three as well because of the reciprocals. Okay, so then the take, that's a T, so that tells us in quadrant 3 that tangent is positive. And then lastly, quadrant 4, the C, tells us that cosine is positive. So if you remember this, and you remember how to go back to the first quadrant angle that's the same, so you know those values, then you can actually find the entries on that chart pretty easily. So let me walk you through one. And we're going to do this. Let's say we want to know what is the cosine of 7 pi over 6. All right, now I'm not going to look at the chart. I could, right? I could easily just pull that chart up again and we could go take a look at it, but I'm not gonna. We're actually gonna build it. We're gonna think through it so that we can, so I can show you how all you need to know is the first quadrant. All right, so we're doing cosine of 7 pi over 6. So the first thing you should do, step number 1, is figure out what quadrant are we in. So the question is, where is 7 pi over 6? At first, this is going to be challenging because this is new to you, especially in radians. But let's remember what the delineators are. The y-axis was pi over 2. The negative x-axis was an angle of pi. Pointing down was 3 pi over 2. And then the positive x-axis was 0 or 2 pi, or it could even be 4 pi or 6 pi or whatever. But let's just kind of go here. So let's think about where 7 pi is, 7 pi over 6. So here's what I do. I forget about the pi, and I think about just the fractions, right? So pi over 2, this is 1/2. The pi, that's 1. 3 pi over 2 is 3/2. This guy's obviously 0 or 2. So thinking about this without the pi, just because I think it's a little bit easier, that's 7/6. So where does 7/6 lie in here? Well, it's bigger than 0. It's bigger than 1/2. Is it bigger than 1?
Yes.
Yeah, that's pretty easy, right? It's an improper fraction. The top is bigger than the bottom, so it's bigger than 1. All right. Is it bigger than 3/2?
No.
All right, so that one's no. The way to check that is think common denominators as sixths. This would be 9/6. So we're not that big. So I'm somewhere between 1 pi and 3/2 pi, which means that we're in quadrant 3. All right, so that one's in quadrant 3. Cool. So now what does that tell me? And why did I start there? Well, I started there because this is going to tell me the sign, the plus or minus sign on this cosine. Since I'm in quadrant 3, in quadrant 3, tangent is the only one of the big three that's positive. So this is going to be a negative number. It's going to be a negative, which means it's going to be the negative of, well, it's going to be the negative of the cosine of pi over 6. So that's the second thing I do. So once I figure out the quadrant, I attach the sign. So I'm going to put here, attach the correct plus or minus. Then I go to the first quadrant. And that's what I did here when I went to pi over 6. So why pi over 6? Well, because that's the bottom of this fraction. We've already seen that pattern. So now I just need to know the cosine of pi over 6. All right. So remember if we just know the first quadrant ones, we're good to go. This is what I mean. So the cosine of pi over 6, if you think about the chart and where this pops in, right? We had sine, we had cosine. The sines went 0, 1/2, root 2 over 2, root 3 over 2, root 4 over 2. So the cosines do the reverse. So the question is, which one is pi over 6? All right, well, let's start with 0. And you're going to get these down pretty fast. It goes pi over 6, pi over 4, pi over 3, pi over 2. So cosine of pi over 6 is root 3 over 2. So that means that the cosine of 7 pi over 6 is negative root 3 over 2. Whew. All right, so let's just kind of take stock here for a second of what's going on. There were a few steps to this, right? Obviously, we had to figure out where we were so that then we could remember which of the plus or minuses do we have for that specific function. And then we had to be able to go back to that first quadrant and remember that angle. Now, do you have to do it this way? Absolutely not. You can have that chart just memorized, right? And if you're someone who's got sort of like a photographic memory, cool. I am envious of you because being able to memorize that chart is impressive. I don't have it memorized. I don't. Even though I've been doing trig, like I've told you, for like 30 years, I don't have it memorized. This is still my thought process. I think about, okay, where am I? What's it related to? And I can come back to it. It's much faster for me because I've been doing it for 30 years. So if you like this kind of thought process, cool, use it. If you don't, cool, use something else. But the better we are at being able to get these numbers, the easier everything else is going to be. Okay, so cosine of 7 pi over 6 is minus root 3 over 2. And if we go back to that trig value chart, 7 pi over 6 cosine, hey, look, is minus root 3 over 2. All right, so it will always work. You can always build your chart this way. Okay, so any questions on that kind of mental process of finding that solution or finding those values?
Could you go back to that other screen just for another second?
You betcha.
Just copy it down. Thank you.
I'll pull that guy back up there. All right, and don't forget that this is being recorded, so it'll be on the video that you can access on YouTube. You can always come back and look at this. All right, so cool. Now we can always find it, but notice how it comes back to the first quadrant. It's all about knowing that first quadrant angle that's like the one that we're dealing with. Well, because those first quadrant angles are so important, they actually have a name. And they're called reference angles. So let's talk a little bit about that. All right, so I'm going to go ahead and clear this screen. Like I said, you can come back and look at the video and see it if you need it. All right, so reference angles. Again, just what they are. A reference angle is a first quadrant angle that shares the symmetry with your given angle. So the only difference is going to be potentially pluses or minuses on the coordinates of the point on the unit circle. So let me go here and just show you, given, say, a second quadrant angle or a third quadrant angle, fourth quadrant angle, how you can find the reference angles. Okay, so let's take a quadrant 2 angle, for example. So here's the terminal side of a quadrant 2 angle. And we'll just name it theta. So we've got a name for it. So if you think about the unit circle, draw one on here, unit circle, everything is determined by this point right here. You find the coordinates of that point. The x coordinate is the cosine, the y coordinate is the sine, and then everything else follows. Okay, so what we're looking for is the angle that shares this symmetry. So that's going to be the one that has this point right there. So let me change the color. I could say green. So this one right here, this is the reference angle. It's a different angle, right? The terminal side's in a different location, but it's the one that we can reference to get the trig values for the second one, right? The sines are going to be identical. The cosines are going to be opposite, pluses and minuses. The tangents are going to be opposite, pluses and minuses, and so on. Okay, so here's the question. How can you find that angle given your second quadrant angle? Well, it turns out that it's pretty easy. From the symmetry, whatever this reference angle is, that's actually the same as if we were to rotate from the negative x-axis up to our original angle. Hopefully you can see that. Imagine just taking that image and folding it over. We'd see that because of the symmetry, we get that. Okay, so how are we going to get the reference angle? Well, it turns out that if we're in quadrant 2, this is all you have to do. Okay, so if you're in quadrant 2, the reference angle, it's going to equal pi minus theta. All right, so why is it pi minus theta? Well, if we were to rotate pi, we're halfway. We've gone too far. So we're going to have to come back. All right, so if we subtract off our angle from pi, we're left with the reference angle. All right, so that's how we do it if we're in quadrant 2. It's pretty easy. All right, if we're in quadrant 3, so let me take another color here and go into quadrant 3. So we're going to be looking for, again, the point that shares the symmetry. So we're looking at this guy down here. So now this is my theta. My reference angle is now going to be this one. So what I know is that if I take pi and I add my reference angle, I'm going to get the angle that I started with. So if we use that, we find out that in quadrant 3, the reference angle, that's going to equal theta minus pi. So if we remove that half rotation, what's left is our reference angle. Real quick, think about the one that we just did, where we had 7 pi over 6. If I subtract pi from that, this is 6, 6. So 7, 6 minus 6, 6 is 1/6 pi. So we didn't actually do that subtraction because we had already seen a pattern of looking at the denominators of those fractions. But this is how you can do it given any angle. If it's in quadrant 3, just subtract pi, and that's your reference angle. All right, so that's how we do that in quadrant 3. If we're in quadrant 4, we're looking for this point. So let me draw yellow guy. So now our theta is this. Our reference angle is now here. So we're almost to 2 pi. We're just a little bit away from 2 pi, right? And so the way that this works out, if we use the formula or want a formula for it, in quadrant 4, the reference angle is going to be 2 pi minus theta, because it's the same idea as quadrant 1. We're a little bit shy of going all the way around. So we just subtract our angle off. And I guess if we want to be complete, because I don't have anything here for quadrant 1, but quadrant 1's kind of silly. Because if you're looking for a quadrant 1 angle that's representative of the quadrant 1 angle that you've got, well, it is itself. So whenever you're in the first quadrant, that's good news. We like those. We don't really have to think about first quadrant angles. It's when we're in the other quadrants that we need to bounce back and find what they are. Now, all these formulas I just gave you are in radians, right? How are these going to change if we're in degrees? What's the difference, say, in this red one if it was degrees?
That's 180.
Yeah, we just changed that pi to 180. So if you were in degrees, it would be 180 minus theta, right? And then similarly in quadrant 2, this would be theta minus 180. And then for the yellow one in quadrant 4, instead of 2 pi, it would be 360. So that's how you handle it if you're in degrees. So one of the things that you're going to be asked to do is find reference angles for various angles. The reason being, it's going to help you figure out the trig function values for them later. And so just depending on where you are, you do exactly this. So let's try one. Let me give you an example here. Let's find the reference angle for, let's get, well, and I'll even be nice. I'll give it to you in degrees. So let's try 117 degrees. All right, so first things first, we have to figure out which quadrant, so we know which of these things to do. So what quadrant is 117 degrees in?
Quadrant 2.
Good. So this one's in quadrant 2. It's way easier to figure these out in degrees, right? Because we know it's got to be, it's bigger than 90, but it's smaller than 180. All right, so this one's quadrant 2. So we go to the quadrant 2 formula. And for degrees is going to be 180 minus 117, which I think is 63 degrees. So that's the angle, the first quadrant angle, that shares a symmetry with 117 degrees. So we know that the trig function values for 117 are going to be the same as those for 63. just with potentially different pluses or minuses. Okay, so that's why we care about reference angles. Yeah, they're pretty useful. All right. And it's really that easy. It's just a matter of remembering which of these things to do. And I'm a real visual guy. I think about this picture, and that helps me see what I need. Just remember the reference angle is always how far you're going from the x-axis, right? If you look at these light green arrows, every one of them was rotating away from the x-axis. So just think about how you have to rotate off the x-axis to get where you are, and that will help you find your reference angles.
Real quick, can I ask a question?
Of course.
For quadrant 4, the reference angle formula, is that 360 minus theta?
Yeah. Yep.
Okay.
And the 360 is just coming from the fact that it's a full circle in degrees, full rotation. All right. So, cool. There's some more, something else we can use to help us when we're dealing with this chart. All right. So, before we dive into these things as functions, I want to share with you just one more thing, well, a couple more relationships between the trig functions that come from the fact that they're on the unit circle. So I'm going to go ahead and clear this and make a new whiteboard. All right, so again, let's think about the unit circle. We'll draw it again. So who here remembers how to get the equation of a circle? Has nothing to do with trig.
2 pi r.
All right, so 2 pi r gives you the circumference of the circle.
Oh, pi r squared.
Pi r squared gives you the area of the circle, but I want the equation of the circle, like the things with the x's and the y's in it.
Oh, it's like x minus k squared. It's okay, x minus h squared plus y minus k squared.
Okay. And do you remember what it equals?
R squared.
R squared, beautiful. Okay, so this is the equation of a circle where h and k, those are the coordinates of the center, and then r is the radius. All right, so that's just in general what we get for a circle. But if we look at the unit circle, all right, so now both h and k are going to be 0 because that's the center of our circle, and the radius is equal to 1. So let me just simplify this a little bit. Now we get x squared plus y squared equals 1. So that's the equation of that circle. And when you talk about the equation of something, of a graph, we're just saying that the points on the graph, when you plug in the coordinates of all the points on the graph, they have to satisfy this equation. So you take any point on the unit circle, you square the x, you square the y, you add them together, you're going to get 1. All right, now I don't know if you remember where this came from, but if you were to look at just some generic point here and draw this right there, it's a right triangle. That's length x, that's length y. Sorry about that. I can close that off a little bit. That's length y, and this is length 1. It's the radius. Well, if you do the Pythagorean theorem on that, you get x squared plus y squared equals 1 squared. So that's actually where this equation for circles comes from, is just doing the Pythagorean theorem on a radial line from the center out to one of the points. Okay, I do this for a couple of reasons. First, check this out. This triangle has the same relationship as this circle. So mathematically, algebraically, circles, triangles, they're really the same thing. I know this hurts. This really hurts the like 4-year-old part of your brain when you're taught all the shapes and you're like, no, a triangle and a circle are different. But mathematically, structurally, they're identical. That's why we can even do stuff with a unit circle in terms of the trig values, because they're structurally the same. All right, well, that's just sort of an aside. What I really want to show you here is think about this equation for the unit circle, but let's change it into trig functions. And what I mean by that is that with the trig functions, remember that, for example, sine of theta was equal to y, and cosine of theta was equal to x. So we can actually fire those in here into this equation, and what we get is cosine theta squared plus sine theta squared equals 1. All right, now this doesn't matter what the angle is, right? Because no matter what angle we had, wherever we ran onto the circle and got a point xy, we know that when we square them and add them together, we get 1. So that means that this is an identity, right? This is something that's just always true, no matter what your angle is. Now, what you're going to see when you see this written is you're actually going to see it written like this. The reason that I'm starting with sine instead of cosine is arbitrary. That's just because that's sort of how everyone remembers it. But I do want to talk about this squared, the fact that that squared kind of came inside here. And this is how mathematicians always write powers of trig functions. So for example, no, that's too light. Let's go. All right, so if we had, say, sine of theta to the 4th, mathematicians will write that like this. They'll bring that exponent in so that it's between the trig function and the angle. And what this is telling us is that we're taking the sine and then raising it to the 4th power. If that 4 were over here, again with the 9, my stupid stylus. Right, so it's like that. What this is saying is we're taking the angle, taking it to the 4th power, and then doing the sine. So notice that those are different, right? This means different things. It's a difference in the order of operations. And so because mathematicians like to be really precise, we also don't want to have to write all these parentheses and everything. We've developed this shorthand way of saying what we're doing when we take a power. Okay, so I just want you to realize when we write this, when we write the sine with squared and then theta, that means we're taking the sine of theta, whatever that number is, and then squaring it, as opposed to squaring the angle and then taking the sine. Okay, so this guy right here, its name, you're gonna love this, is the Pythagorean identity. Because it's the identity that comes from the Pythagorean theorem. Okay, this identity, I promise you, you're gonna remember. It's like the one identity that everyone remembers from Trig. Go find someone who took Trig 20 years ago, ask them about identities. The first thing they're going to say is, oh my God, I don't remember any of that stuff. And you say, you don't actually remember anything? I'm sure you remember something. And they'll probably go, yeah, there's some sort of like sine squared plus cosine squared equals 1. Like this is the one that everybody remembers. It's also really useful. And we will see that as we go forward. All right. But you want to know this one. Sine squared plus cosine squared equals 1. All right. So let's put a little box around it. But it's really easy to remember if you just remember the Pythagorean theorem. X squared plus y squared equals 1. X is cosine, y is sine. All right, so we can actually add that now to the list of identities that we know. So let me just remind you what we've seen so far. All right, so in terms of all the different identities, hold on a second here. I got to move some windows on my computer around. All right, so we had the reciprocal. So those were how we found the others of the big three, right? That secant is 1 over cosine. Cosecant is 1 over sine. And cotangent was 1 over tangent. Okay, so we saw those really early on. All right, there are a pair that I want to put down over here called the quotient identities. And I actually showed you one of them today. And it was that the tangent is equal to the sine over the cosine. And that's pretty evident from the unit circle definition, right? Tangent is y over x. The y is sine, the x is cosine. So tangent is sine over cosine. So we call it a quotient identity because quotient just means fraction. So tangent is a fraction of sine and cosine. Now, I didn't tell you this one, but I'm sure it's going to come as no surprise to anybody that the cotangent is actually the cosine over the sine. It's x over y, or you can think it's the reciprocal of this one. So if you flip it over, you get that. But we call those two the quotient identities. All right, and now we'll add to it the Pythagorean. Okay, so let me just make another little row here. So Pythagorean. So we've got sine squared plus cosine squared equals 1. And you'll actually see that if you were to take any of the points on our chart, any of the x and y pairs, if you square both of them and add them together, you always get 1. It always happens. All right, so just comes naturally from the definition of the unit circle. But it turns out there are actually 2 other Pythagorean identities. There are 2 other identities that we can get from this one that, while are not quite as useful, they're still definitely useful, and you probably want to know them. So let me just clear some space here to show you how we can get them. So here's what we're going to do. We're going to take that Pythagorean identity, and we're going to do a little bit of algebra on it. So what I'm going to do first is I'm going to divide everything by cosine squared. And if you ask me, why are you dividing by cosine squared? I'm going to say, because it leads to the next identity. It's, you know, mathematicians like to play with things. They like to just fiddle around algebraically and see what happens. Well, check this out. Watch what happens. Okay, so first of all, this middle term, cosine squareds cancel. So anytime you take something and divide it by itself, what you get is 1. So that thing just becomes a 1. Now, 1 over cosine squared, that's the same as 1 over cosine times 1 over cosine. Similarly, sine squared over cosine squared is the same as sine over cosine times sine over cosine. And there's a reason that I wrote them out this way. Because 1 over cosine is another trig function. If we come over here and look at the reciprocal, 1 over cosine is actually the same as secant. So this is secant times secant, which is secant squared. Now over here we have sine over cosine. Well, sine over cosine, that's tangent. So I've got tangent times tangent, which is tangent squared. And that is your second Pythagorean identity. It shows you a relationship between tangent and secant. So there's a relationship between sine and cosine, but there's also one between tangent and secant. All right, well, there's a third one. And this one, again, we're going to start with the Pythagorean. But this time, I'm going to divide everything by sine squared. And again, why sine squared? Well, because it's going to give us what we want. So let's see what happens. Sine squared divided by sine squared is 1. Those things cancel out. I now have cosine squared over sine squared. So that's cosine over sine being squared. Cosine over sine, if we come over here to the quotient identities, is cotangent. So that piece is cotangent squared. And then if we go to the reciprocals, 1 over sine, over here, that's cosecant. So this is cosecant squared. So the other two Pythagorean identities, they are like the first one. They're just showing now relationships between other sets of functions. All right, so we've actually started building a pretty big list of identities. Oh, but this is small. Our list is going to get so big by the time we're done. I mean, there's another set that I didn't put on here. Remember the cofunction ones? Right, that the sine of theta is the same as cosine of pi over 2 minus theta and so on. So we also had those. But these are kind of our new ones that come from looking at this as a unit circle. But this is going to help us when we start talking about these things as functions and what they look like and what they do. All right, so let's go back and look at that chart. I'm going to hop back over here. Look at this chart. And actually, let's pull up a new one because this one's pretty cluttered. So there's another guy. So here's what I want to do. I want to look at cosine. I want to look at cosine, and I want to think about it as a function. I want to think about it as a function, meaning look at domain and range and intercepts and all of that good stuff. Okay, so since we're thinking about cosine, we just need to remember that we're looking at this column right here. Right? And really this column came from, it was the x coordinates, right? The x coordinates of the point on the unit circle. All right, so first question is, looking at that list, what's the biggest number you see? What's the biggest number in that column?
1.
All right, looks like 1 to me is the biggest as well. Root 2 over 2, well, 1/2 is definitely not as big as 1. Root 2 over 2, that's like 0.7 something, 0.707. Root 3 over 2, I think is like 0.866. All right, but they're not as big as 1. So 1 is definitely the biggest, and then we get some negatives, which are smaller, but looks like 1 is probably the biggest. And then similarly, what's the smallest number?
-1.
-1. All right, so what we've seen just in our glance at these nice functions is that cosine only gives us numbers that are between plus and -1. So the question is that true? Is that the case that there's never going to be a number bigger than 1 or smaller than -1? All right, well, let's think about this as a function. Let's draw something new here. So here's the function that I want to think about. I want to think about f of theta equals cosine of theta. All right, so theta is going to be our variable. That's just the angle. And so I want to look at this as a function. So first, let me just remind you some things. What do I mean when I talk about the domain of a function? What's a domain mean?
It's how high and
Aren't
low
those
x.
its x coordinates?
Okay, so I heard x coordinates, and then somebody else said something, and I apologize for not hearing that.
It's the lowest and highest s.
Okay, so when we talk about domain, we think about a biggest and a smallest. And I don't remember who that was that said x coordinates. I don't want to think of it as x coordinates, but let's think about it as the stuff we plug in, right? Like if you're thinking f of x, it's the x's. But the domain, this is the set of values that can be plugged in. Meaning those are things that when we put them in, the function actually makes sense. We don't run into any issues, right? Like issues like we've seen division by 0, square roots of negative numbers, things like that, right? Those are not domain values, but as long as you can put it in and your function works and it spits something out, that's your domain. Okay, so then what's the range? What does that mean in general?
It's the output of the function.
Good. Yeah, so if the domain is a set of values that can be plugged in, the range is the set of values that come out. All right, so let's investigate that here. Let's investigate the domain and range of cosine, thinking about it this way. So the set of values that can be plugged in, if we're talking about cosine, this is angles. So domain is going to be angles. And then the range, it's the set of values that come out. I'm going to put here x coordinates. Because remember, cosine is the x coordinate of the point. So to help us investigate that, we are going to look at a little guy here. Basically what this is, it's a unit circle. I can move my dot around. You'll see that what I have here is my angle given to me in radians right now. It tells me the point that's on the unit circle. So that red dot is 0.903, 0.431. Right? I can change it to degrees if I want, but I don't. I want radians. I also can pick different functions. I've got cosine, sine, and tangent. Since we're going to be looking at cosine, let's look at cosine. So again, remember, cosine is our x coordinate. So like for this point right here, whatever this angle is, 0.445 radians, the cosine is 0.903. All right, so let's just kind of watch what happens to these values as we move around. So we already know that that x coordinate is 1 when we're out here at 0 degrees or 0 radians. And as we start moving in this direction, what happens to that x number? What's going on as I spin around this way? Oh, went too far.
It gets smaller.
It got smaller, right? It went from 1 down to 0, and I just cannot quite get it right exactly there. Close enough. Oh, there it is. Yay. Okay. So it went from 1 down to 0 because the x coordinates on these points, if you think about following that red dot, the x coordinates, that red dot got closer to the y-axis. So it started at 1 and it got smaller, got to 0. Well, now when we start going down into the second quadrant, you can see that they're now negative, right? Cosine is negative, and it continues all the way down to -1. As we continue our journey, it stays negative, but gets closer to 0. Okay. Then it turns positive and gets bigger up to 1. All right, so just think about that dot. As we just keep rotating, going around and around and around, it keeps bouncing back and forth the x values from 1 down to -1, back up to 1, down to -1, back up to 1, down to -1. Boring. But notice that we get every number between plus and minus. Every one of those values is going to show up somewhere. It just keeps repeating. All right, so if we go back to what does that mean in terms of domain and range? These are the ranges. We're talking about the x coordinates, right? The x coordinates of the points. And so it turns out that the range of cosine is -1 to 1. So on our chart, we actually saw the biggest value and the smallest value. We didn't see all the values in between, but they do show up somewhere. All right, now I know what some of you are thinking. Wait a minute, the domain is the x's, not the range. Yes, when we write f of x, you're right. But remember these x coordinates, those are not those x's. We're plugging in angles. That's why I specifically wrote here, the domain is the set of angles and the range is the set of the x coordinates, because that's how cosine was defined. Okay, so x is being used differently here. Now, in terms of the domain, the question is there ever an angle where we're not going to be able to get the cosine value? So here's how to think about it with the unit circle is there ever an angle whose terminal side does not intersect the unit circle? Well, that's a pretty easy, well, no, of course. Everything that comes out of the origin, you draw a ray, is going to intersect that circle. So it turns out that the domain of cosine is actually -infinity to infinity. You get all real numbers. You can plug in any angle you want, and you are going to be able to get a cosine. And that cosine is going to be somewhere between -1 and 1. All right, so there's the domain and range of cosine.
I got a question, Bruce.
Sure, go for it.
Is the reason why I use parentheses versus brackets because one of them is an estimated value and the other one's an exact value?
No. Whenever we do intervals, brackets mean we include that endpoint. So the range includes the value of -1 and 1. If you use a parenthesis, that would just mean that you get really, really close to -1. You just never quite get there. But we do get values of plus and -1. So that's why these have brackets. The infinities always have parentheses because there is no end. There is no last number. So there's no last number to include. So we always put parentheses on infinities.
Okay, sweet. Thank you.
Yeah, you're welcome. All right, so there's for cosine. Now let's look at sine real quick because we can kind of make the same argument here. Now when we talk about the domain and the range, the domain, this is going to be the set of angles again that you can plug in. And the range, this is going to be the set of y coordinates. And it's the y coordinates because that's how sine was defined. All right, well, in terms of the domain, I think it's probably pretty easy to see that it's the same domain. Because is there ever an angle whose terminal side does not intersect the circle? No, of course not. Okay, but then what about the range? Well, let's go back to that kind of going around in circles thing. That's hopefully everybody can see it. And I think that's going to make me, oh yeah, that worked. Okay. So let's change it now to sine. But now remember what sine is the y coordinates. So as I go around in the circle, think about what the y coordinates do. I go from 0 up to 1, down to 0, down to -1, to 0 to 1, down to -1, 0 up to +1, to -1, to +1, to -1. Notice it's doing exactly the same thing as the cosine did. The y coordinates just keep bouncing back and forth between plus and -1. And so we actually see the identical range. For the range of sine, it's also going to be -1 to 1. Because as you go around in that circle, your y coordinates they're somewhere between those values. All right, so there are the domain and range for sine and cosine. I just noticed on the clock that we're out of time. So we will pick this up on Monday. We will continue the discussion and we'll talk about the other trig functions, talk about their domain and range, and then we'll start graphing them. And we'll start seeing, looking at things like intercepts and asymptotes and all the other features that you've ever talked about with graphs. Of functions, but there's a little bit more we can do with the trig ones because of the fact that they repeat. All right, so just a couple of reminders. Homework on Monday, the Nexa is due Monday night, so make sure you get in there and keep plugging along with it. Other than that, I hope you guys all have a wonderful weekend, and I will see you all on Monday.